Okay, in the last class, we learned about what? What we learned last class? We learned about technology based on the scientific knowledge, and then to read the scientific knowledge, you need what we call, you need to have this knowledge on how to use unit, how to use the prefix, do conversion, and so on. So, once you're done with the knowing about prefix and the units, once you're done with the units and prefix, only then you can go to the science itself. We still under the technology part, okay. So now in the previous class, Fatih said, where is Safwan Fatih? Not here. Safwan Fatih said that one type of technology is phone, right? Right. It's a phone. Your phone here, your smartphone. Okay, so what is the basis for this phone to work? What is the basis? What is the science behind this phone? What is the science behind this phone? For example, what is the science behind this phone? Sorry? Electronic, yeah, electronic, but the science behind the electronic? Wave. Because, for example, when you talk to your phone, no matter how loud you try to shout, if let's say the end user cannot hear you, then no use lah. Okay, but if you think about it, if let's say you don't have phone, how far you think that your voice can go? How far? As loud as possible you shout, how far the what we call your sound will travel? So that, let's say this thing. Yeah, Azim. Okay, Azim try to shout to Tania. Okay, Tania. So the most, I mean, I don't know what's the thing, but if you do its correct condition, the most you can go is around 10 kilometer like that. Okay, so the thing is that when you have your phone like this, okay, how then you can convert? You don't shout on your phone, right? You just talk normally. You talk like hello Tania, like that, right, Azim? So and then Tania hear you. Okay, hello Tania. Okay, so the Azim sound soothing, right? I mean, Azim doesn't shout. So how come that level of intonation can be transferred to Tania, which is maybe, let's say, 1,000 kilometer away? Maybe Tania in London, you in Malaysia, So how come you transferring the what we call, what is the, because your sound is a wave, right? Your voice itself is already a wave, okay? And then Tania here also the wave voice, right? But you know that your voice cannot travel so far. So what happened in between? What happened in between here? So that's the basis of the wireless, what we call wireless phone lah. I mean cell phone lah. Cell phone use wireless. Before this, if let's say Azim in the old school just call Tania using this line, so we know that whatever voice that Azim tried to speak, it will sort of like what we call, it will sort of like because voice itself is like the vibration of air, right? Where is my? Oh, okay. So when I talk, if let's say using the normal phone, line phone, this when you talk, you basically you vibrate this diaphragm lah, diaphragm inside the what we call inside the phone, and then this will convert into the electrical signal, and then this electrical signal will be what we call translate into the electrical pulse and go to this what we call to London. So that is when you have the line connecting between you and Tania. But now there are just nothing in between. So the idea, the science behind the modern telecommunication is basically wireless lah. But how come you transmit this to this? How you sort of like throw this thing to this? Anyone? Huh? Huh? Wire? Where is wire? Where is wire? There are no wire. It's London. Where is wire? Satellite. What you give to satellite? So satellite, let's say satellite is here. This is satellite. Satellite. So how you transmit your voice? You know that your voice cannot go far than 10 kilometers. So how you go to satellite? Huh? Amplify? So amplify, how much amplify you will do? Because if you amplify, you go to satellite, and then satellite bounce back to whatever Tanya, there are a lot of amplification will be done lah. So that is not really effective, cost effective. You can amplify the voice, but the medium is like empty. It's like to go to satellite is like up to the sky is far more than 10,000 kilometers. It's more than that. And go back to Tanya is like, and you need to understand that in the world, everyone do this thing. And then you cannot really rely on one satellite to do all this thing. Okay? So the idea is that for this to work, this voice, what we call this wave here, you need to transform it into another wave form, which is what we call radio wave. Radio wave. Okay? When we, the wave that normally when you switch on the radio, right? Radio. So that is waveform, one type of the waveform. So this radio wave, there are two things now. You have voice. So you have voice now, your own voice, which is a sound wave. And you have what we call the radio wave. You have another one. This is under electromagnetic spectrum. So this EM, we call it radio wave. Radio wave. Okay. Radio wave have nothing to do with sound. You cannot hear radio wave. Okay. In fact, radio wave is like light. It's part of the spectrum of the light lah. So if you look here, you can see here, radio wave here is share the same properties with the visible light. So it's like visible light, but have a lower, what you call, lower energy lah, and bigger wavelength. So when you have this thing, the advantage of using this thing is because it can travel in vacuum. So it's not really affected. It will affected by other things like a building and so on, but it's not much lah compared to the voice. Because the voice itself is air pressure. It's basically the voice here. It's basically a vibration of air particle. So when, for example, Azim shout to Tanya. So this is Azim. So this Azim. What is this thing? So hidung, mulut. Shout to Tanya. What happened is that this what happened. So you have air particle here, air particle around you. Okay. So this air particle will be compressed and decompressed and then compressed again depending on your intonation. So you get this what we call this region. We call it rarefaction. Rarefaction, and this region, meaning that the molecule of air compressed together as compressed region lah. Compressed region. So you get this thing, and the pattern that you have here is basically correspond to what you say. That is because you talk, your what you call Adam's apple will vibrate, right? So it's sort of like correspond to that. So this thing, this air particle will not be travel so far lah, because over time it will peters out. Peters out. Okay, because the air have resistance and so on. But when you have this radio wave, it's something different. It doesn't rely on the air. It's just the wave lah. It's just a wave. It's a wave. It's not like the air particle. So that's the difference. Your sound is because of the vibration of particle around you, and radio wave is nothing to do with the sound at all. Meaning that even though the name is radio, but it's nothing to do with the sound. It's just like the electromagnetic spectrum is just electro, which is you have electric and also the what we call the electromagnetic, electric and magnetic. You have seen before. I mean, I think you have seen before what is electromagnetic. Electromagnetic spectrum is basically a combination of electric and magnetic, right? So let me put here EM wave. Okay, so you can see there. You can see here. It has this what we call the electric and also the magnetic component. So that's what so it doesn't rely on the air particle and so on. Because when you have air particle, suddenly if like it's rainy, then of course you cannot really hear, right? So that's the thing, the reason why people use this lah, the what we call the electromagnetic. They need to convert into the radio wave. Radio wave can go to the ni lah. And one thing about this radio wave can penetrate what we call the wall and so on. The wall, especially the long wavelength, especially this thing when you see here. How to move? For example, here, how to put it? Okay, so for example here, this big wave can penetrate the what we call the wall and so on. For example, if you talk here, people outside cannot hear, right? If you use the voice, the sound, you cannot go out because the air, this particle of air cannot go out. But if you have radio wave, you call here Tanya outside. So this radio wave will go pass through this what we call this wall lah. Okay. Okay. So okay, until that it's okay. So today, why I talk about this wave thing? Because the wave will be useful in as a tool to probe the world of unknown. Even though it seems like it doesn't have anything to do with bionanotechnology, but the understanding of wave will allow scientists to sort of like probe the unknown. In fact, if you see most of the Nobel Prize, among all the Nobel Prize, majority of it is based on X-ray, SRD, X-ray diffraction, meaning that they use X-ray to try to find the structure of something. For example, the DNA, your DNA, the double helix thing, they found it, scientists found it because of the X-ray. They use X-ray to look. They cannot use the what you call the visible light because the visible light is too big for that. So they use X-ray. Okay, and also what else? I think during your what you call during your lab session, you have used this thing, right? UV spectrophotometer, right? Spectro for what? For what? To find what? UV vis. The name itself is based on that lah, UV and vis. Meaning that again you use a wave to do something. And later on when you want to see something that very small, like for example bacteria, let's say you want to see bacteria, you use microscope, right? Microscope, and this microscope use visible light. If you want to use a virus, for example the COVID-19 virus, you cannot use normal microscope, this is optical. You need to use electron microscope. Okay, this electron microscope using wave also, but this wave is not there lah. I mean, this wave is basically wave emanated by the electron, because the electron, the atom, the electron here, it can emanate its own what we call its own wave lah. So the basis of the looking thing using electron microscope is basically the wave also. So this electron wave lah, electron wave. Later we will see lah in detail about what does it mean by electron wave and so on. What else? What else? Gamma ray. So gamma ray, you have Petri dish, right? You have Petri dish. You do the FIP. Most of you did the FIP in the lab now. So if you want to grow something on the Petri dish, let's say this Petri dish, you want to grow something, for example, grow bacteria on the Petri dish. You need to make sure this Petri dish is sterilized. So they use this gamma irradiation to kill the virus or whatever lah, to kill all the microbes and inside this thing lah. So that when you do plating, when you do agar, that agar will not contaminated, because when you deal with the living thing, the most problematic thing is to prevent the contamination. If you use a normal plastic Petri dish that is not sterilized, then the probability for you to get contamination is big lah. Because this Petri dish, if you look, is made by plastic. You cannot heat it. Normally, if you have like something steel or whatever, you put in the autoclave, fine. But this Petri dish is made of plastic, you put in the autoclave, then you get nothing lah. So that's why they use gamma irradiation, meaning that the light, but this light have higher frequency. The higher the frequency, the more energy it will able to sort of like knock off the electron inside the atom, knock off the electron inside the virus, and then the virus mutate and die lah. So that's the use of gamma. You also use the infrared. I don't know, some of you might use the FTIR. Have you ever used FTIR before? Anyone here? Okay, Saida or Jannah. Saida, Jannah. So for example, IR. So sometimes, for example, you want to know, you learn in the organic chemistry, they are like phenol group, they are like, apa lagi? Alcohol group. They are, for example, they have alcohol group, apa lagi? Ester macam mana? Ester group, lagi apa lagi? Functional group, example of functional group. Carboxyl, for example, this is either you can get COH or you have COR. Okay, so basically this is, I don't know lah whether you remember or not, this aldehyde, this is ketone, and so on lah. So basically, how people know that inside this paper, let's say I have this paper, right? How do I know that inside this they are hydroxyl group? So the way how they do it, they take this paper and they put inside on the equipment. We call it, that equipment is FTIR lah, FTIR, Fourier transform, Fourier transform. This Fourier transform is basically the mathematical way to no need to too much lah, because it's just a mathematical way to transform certain wave to another version lah. So IR here is infrared, that's infrared. So how they know that inside this they are like OH group or whatever group, O group or whatever group, is basically they put it inside a machine that's like this. You have the machine like this. Machine is very simple. You have like a machine here, the sample placeholder here, they have sample placeholder, and then you put your paper here, and then there are another arm, for example, there are arm here, so arm to press it down. So basically now you have something like this is sample holder, you have what we call the sample, and then you have arm to hold it tightly. Okay, so the IR will be sort of like what you call irradiated from here. Irradiated, I don't know what the term, but basically you hit the sample with the IR from below, and then because the sample is so tight, I mean that it have less, what we call, the gap is almost not very micron gap. So when the IR light or whatever energy goes here, it will go through into the paper. If I make it bigger here, where's my green? If I make it bigger here, so you can see inside the paper here. So this paper, let's say this paper, and inside here is like, normally they use diamond lah. They use diamond here. They use diamond here. They use diamond, and then on the top is just basically something to hold lah, something to hold. We call it arm lah, arm. So basically they will sort of like, the IR come from here, and then they goes inside the diamond, because diamond is transparent. It goes inside, and then it sort of like goes inside the paper, and then because of the internal what we call internal refraction of this diamond, because diamond, that's why diamond is shiny, because the light goes and then refract. Okay, it goes back to here, and then goes back 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 there, out. So this IR. So what happened now here, so they use IR. So what this IR does, this IR is basically the electromagnetic energy that is higher than, not higher, this is lower than visible light. What will happen, the molecule inside this paper will sort of like will vibrate. Maybe like vibrate here like that, maybe vibrate like this, and maybe vibrate like this, goes here and goes, it vibrate. The molecule inside the paper vibrate. Each material have their own vibration. For example, the hydroxyl group, they have their own what we call specific vibration. And from this, you get the what we call the spectrum, and then you know this will give you what in what, because this spectrum, whatever you see from the result for paper, it will give something like this. For other thing, it gives something maybe different. So that's the idea how people know this inside this they have whatever functional group or not. It's based on using IR to vibrate the molecule inside the sample. So that's basically the use. And microwave, you know microwave, right? You go to your home and you cook. So the idea of microwave is try to vibrate the molecule, the water molecule. Inside any food, normally, you have the water inside that. You have chicken, inside chicken you have water. And then when you put into microwave, the wave will sort of like try to vibrate the water molecule. And you know temperature is basically the function of molecule vibration. The faster the molecule vibrate, the hotter it is. So that's the idea of microwave lah. Now we go to radio wave. Radio wave, you see, is much bigger than other stuff. So this radio wave, when it is so what we call so big, it can travel farther lah. So that's one of the idea of the radio wave lah. So they use this radio wave to what we call to transmit data in the long range lah normally. For example, when you switch on the radio in your car, normally you see, for example, let's say apa radio station you normally switch on? Any radio station? Era. What dia punya ni? 103.30, right? I don't know lah, but maybe like this lah. So era, megahertz or gigahertz or whatever? Megahertz. So this is basically, this thing shows the what? Shows the radio wave, the frequency of radio wave. So this is basically frequency of radio wave. Radio wave. So you have something like this. So let's say this is 1 second. From this to this is 1 second. 1 second. So what does it mean is that the radio wave for era station that's transmitted by the era, they oscillate 100 million times per second. So you have like, for example, let's say I will do like this. That is one time, one complete, right? Up, down, one complete. So the era, 1,000 million times. So that is frequency lah. So even this is not very energetic lah. Because if you look here, the visible light is more energetic than the radio wave. Okay, the visible light, the frequency is around terahertz. This is just megahertz. Okay, your visible light here, that's why you don't see the thing, because it sort of like vibrates so fast to the point that you cannot see the thing. So that's energy is what we call in the visible region is around terahertz lah. And then you go to gamma ray, that is what? This what is frequency? So it's an, I don't know, this is what? 10 to the power of 20. So as you can see, that is the use of knowing about the wave lah. Later on, you will see that when we learn about the electron microscope, because after fundamental part, we will learn about the tools, how to look at the nano thing and so on. So that's why I bring you this, the wave thing, because it's important for you to know first, because later on when I explain about XRD or whatever, like this, where is it, SRD and whatever, then I will not repeat this again. Okay. So until now, that is just overview on wave lah. Overview of wave. So any question on wave? Huh? Clear. Apa yang clear? Okay. what to do. Okay, before I go further, I just want to tell you that from visible here until here, we call it ionizing radiation. Okay, from you have this what we call radio, micro, and then you have infra, visible, and then you have what? UV, and then X-ray, and then also gamma. So from here to here, from where? From here to here, this one, from here to here, we call it ionizing radiation, meaning that it can sort of like knock off the electron inside the atom. Okay, this one from here to here is non-ionizing. Non-ionizing, meaning that, for example, the light, right? The light, visible light. So if you have like this light goes to my hand, it doesn't do anything to my molecule and to my the atom, the electron on the atom. But here, for example, UV, you do your work in the lab and you are in the laminar hood, you forgot to switch off the UV. It's happened. What happened is that UV is so powerful in terms of energy, it will go through your hand and then it will sort of like what we call penetrate inside and knock off the electron inside the atom, and that's cause cancer or burn. That's why the sunburn is happen because of the UV from the light, right? From the light. You don't get sunburn in the car. If you think about it, in the car you have the what we call the glass. Regardless whether you coat the glass or not, even if you don't coat the glass, you sit inside the car, you have sun, the UV ray cannot reach you. Because all of these things, in order to penetrate something, it depends on what we call on the material that it need to penetrate. For example, UV, UV. You have car, let's say you are in the car, you have the glass here, and then you are inside here. You will see, regardless whether you coat or apa nama dia? Tinted, you tint or not, this thing. If let's say you don't tint, even though they have sun, the UV will not reach you. Let's say this UV, because the UV will block by the glass. Okay, but the light also, remember, the light and UV is basically the same thing. It just UV have the difference is just the wavelength, but the thing is the same. So the light can go in. So this is visible. So the way same like the radio wave. The radio wave, you have the wall here. Let's say I have wall here. And then you have the radio here. Radio here, and then the wave of the radio will penetrate through through the wall. Okay, but light cannot. Light, even though it have, for example, you have the torchlight here. You try to torch this thing, the light will be blocked by the wall. Okay, because it's not because whether it's energetic or not it can penetrate. It depends on the material itself. Okay, because it's something to do with what we call with the excitation of electron inside the atom lah. Because inside the atom, you see inside the atom, you have the atom here. Let's say the nucleus, and then the electron. You have, let's say this is electron shell or whatever. So let's say the electron sit here. Okay, electron sit here. Let's say lah, electron sit here, and then sit here. So when energy comes, energy can come from this thing lah. We call it energy. When the energy comes, whether this electron will be excited meaning that it moves from one level to another level. Whether the electron excited depend on the kind of energy. Meaning that if the energy is not right, it will not excite. Let's say siapa ada duit. Singgit ke berapa? Bukan. Singgit, anything. Saya tak bawa lah tu, tapi tak apalah. Raya. Okay, thank you. Tak apalah, ambil luar tinggi. Okay, let's say here, you know inside this they are what we call, they are fluorescent inside, right? people check the counterfeit or not, they just put the UV, right? So when this thing, let's say this thing, the electron inside this is this. No lah, I mean inside this, in order to, they are fluorescent material. Let's say the fluorescent material is this. Okay, if let's say you shine with the normal light, for example now, this and nothing happen, right? You don't see anything. What happened actually is that the light have their own color macam ni lah. Merah, biru, biru. Nak senang nak empat-empat color ni. So you see the light have their own what we call wavelength, right? But the wavelength is not sort of like not right in order to excite this thing. So it just go pass through like that, pass through, or maybe reflected or absorbed or what. So it can either absorb or not, but nothing happened to the electron itself. But come UV, let's say this is light, this is light. Come UV come, it just enough energy to sort of like excite this thing. So let's put sini. So this, when it receive energy, because all this thing is energy, carries energy. This thing will somehow lompat apa? Jump to the second, the next highest orbital here. Okay, so that's what happened when the electron receive the enough energy, the specific energy. But on this higher, what we call higher energy level, it's not stable. It's not stable. So over time, this thing will go back down. Will go back down, and then it receive it. When it goes back down, what happens is that it will release the energy. Color sama lah. Pening you. So it will release the same energy as it's received in what we call in the form of a fluorescence. So that's why when you shine the UV light here, what will happen? The electron will gain enough energy to excite to the next level, and then it's not stable on the top, the next energy level. It goes down. When it goes down, it will release the light lah, in terms of fluorescence in this case. So that's why the energy that you shine, saya ambil metal lah. Okay. So that's basically just the run through on the what we call on this energy thing lah. Energy and wave and so on. Okay. Okay. Coming back to this, what we call this thing. Okay. Coming back to this thing. So inside this, when you talk, it will have the microphone inside this. It try to what we call convert that into the electrical signal. Okay, that is normal here. If you use landline, electrical signal just go through cable, because the what you call they cannot use the vibration of your sound to go to move through this thing, because it will peter out. It seems like when you use what you call when you use what you call the string cup. Pernah main tak ni? Pernah? Pernah ke teori ke atau praktikal? Pernah buat praktikal? Teori kan? So basically, if you use this thing, your vibration from the sound is enough to travel to this. But if let's say the distance is too far, it's not enough, it will peter out. Okay? That's why they convert into electrical pulse, go to the electrical ni lah. For the landline phone. For this, it's enough lah. Okay, so let's try. I won't never try lah. Saya nak yang hujung Saidah. Mana Saidah? Saidah ke Nisa? Nisa. Saya selalu ingat you Saidah. Hakim sini, Hakim dengan Saidah. You try buat laju tu pandaran. You try. Sambil tu saya ni lah. Saidah, kasih kat Saidah. Saidah ke? Saidah ke Nisa? Nisa. Nah, pas kat Nisa. Pas kat Nisa. I never try lah, but I want to see lah. I also want to see. Never try this thing, but I also want to see, because normally I see in theory only. Most of you most of you ni, okay, basically you tebuk tengah ni, tebuk dengan paku, nanti saya kasih paku. Saidah nanti dulu. Nisa, nanti saya kasih paku. Tebuk sini, lepas tu pandai-pandai lah, you tahu kan? Pandai-pandai lah. Saya kasi tahu lah kot. Tebuk je. You ada gunting, bagus. Tebuk, lepas tu you just mas ni. Depan. Okay, so you just tebuk macam ni, you masuk macam ni. Sebab ni saya tak nak ambil masa lama sangat ni. So the reason kenapa saya tak buat awal, sebab you akan guna cup ni untuk cakap. So saya tak nak lah nanti you kata saya bawa COVID. So that's why saya tak guna lagi, saya tak buat awal. So you buat, nanti you jangan kongsi ya. Sebab nanti you guna mulut you. So ni you ikat dengan ni. Ni biar dia ni. Nah, pegang. Okay, Saidah jap. So basically here you can see that we use apa? We use benang. Benang apa? Benang apa, Erika? Thread, because the sound travel, the vibration using this is sound, the vibration they what we call, they travel based on the medium. Okay, if you use air as a medium for transfer the sound, it will easily peter out because it will spread out like that. But if you use something like metal or solid, then it's confined in one thing. So that's why sound travel much faster in the solid than the air. And the water much faster also lah than the what we call, on the air lah, in the air. Tahu kan? Saidah Jannah dengan Nisa. Nisa apa? Tu sebab nama tu saya confuse, sebab nama you Saidatul. Saidatul dan Saidah. Okey. Dapat. Mesti. Dia masuk macam ni je. Macam ni je. Lepas tu you ambil ni. Macam ni. Nah. Ikat mana tu tengah-tengah. Ikat tengah-tengah and then you tarik. Okay. So basically I want to see whether I give some secret code to what you call, to Hakim, whether Nisa can hear or not. Okay or not, Hakim? Okay, while they do this thing, let me continue because we don't want to waste time. So inside this, you see, using this string, it can carry the vibration. Fine, for the short distance it's okay, but long distance you need to transform it into the electrical thing lah. Okay, so in terms of wireless, what will happen is that this electric, they don't have like what we call the wire to transmit the 1010, because what happened here, the getaran ni, the vibration here will be converted into 1001111, the bits lah, I mean the information will be transformed to the electrical pulse. But here cannot, because there are no electrical wire in between. So what happened inside this, they will send to the antenna. So basically they send to antenna inside your phone. Inside your phone here, there are antenna. This antenna will convert this thing, the data, the information, into the radio wave. Radio wave lah. So that's why this radio wave, penuh dah Let me padam. Penuh dah. Okay, so that radio wave, because your phone is not high power device, this radio wave cannot go far. You cannot go to the satellite now. Cannot even. The satellite tu, yang satellite you nampak-nampak tu, dia guna benda ni. Pernah nampak tak benda ni? Benda tu. Tu satellite lah. Dia puncak satellite. Your phone tak pergi satellite. Tak kuat pun nak pergi. Dia kena yang kuat ni. Okay. What happened actually, this thing, let me see. Okay. What happened from this antenna, they give this thing, okay, you can see that. They go to this cell tower. So you see the cell tower in Mahala or whatever, like that. And then you have this thing, you have whatever this thing, cell tower. It goes this thing. Okay, it goes to the cell tower first. So this cell towers is distributed across the globe. So your wave your radio wave don't go up. They just go here, the cell tower. The cell tower is distributed across the globe. For example, let's say I open here, cell tower. Let me open first cell tower. Cell tower. Okay, so that is cell tower lah. Mana? Oh, dia tak ni Dia tak ni. Cell tower. Cell tower wiki. Cell site. Yeah, so that's thing. So you can see this thing. So all this thing is the cell towers that normally you see across the globe. Okay. So these cell towers is basically on the globe. For example, this is Malaysia, whatever lah. So this is the Mesir, this Jepun, this America. Okay, so basically the cell tower, they distributed all the way around the globe inside the grid. So that's why this one thing they call it cell. Okay, so they are in the grid. Okay, so that's why your phone they call it cell phone. When they have no wire, they call it cell phone. So this cell tower will communicate to another cell tower that is near, for example, Azim and Tanya, right? Let's say Tanya in London. So this Tanya. This Tanya. This Azim. Okay. So before this, in order to go to the cell tower in the London, it will go through first the cell tower. So let's this Azim. So you can go here first. So it's like pass through, like my molar, pass here, until go to London. Okay. So until it's reached, let's say they are in between, there are a lot lah. So go to the London cell tower, and then from here it will speed back the EM radio to the Tanya phone, and then the process is reverse, meaning that the radio wave will convert into the 10, the information bit, and then the information bit will be transformed to the vibration in your microphone or speaker, and then you hear your Tanya at last, here Azim. Punya susah, jauh cerita dia. Okay, try this first. I don't know whether you can do it. Okay, the thing for this, in order for it to, okay, this thing for example, for this to work, it must be dapat dah. Okay, this must be straight. It cannot be what we call kendur. Kendur apa? Loose. It must be tight, because because when it's loose the information. Go straight. I will give you some value, and then you tell pen, pinjam. Can be, sorry, pinjam So ni. Tak tahu. Okay. Dengar tak? Dengar. Tak dengar? Cuba tegangkan sikit lagi. Okey. Dia dengar. Dengar ke tak? Dia kena rapat. Kena rapat. Okey. You jangan pegang ni. Tak boleh pegang. Dia kena macam pergilah sana, berdiri jalan. Ke belakang. Tarik je. Bukan, ni kendur. Pergi belakang, berdiri sikit, gerak sikit. Ke belakang. Tak, ke belakang sikit. You tu ke belakang, bukan. Oh, you pegang tak dia. You biar je. You ikat tak? Tengok. Oh, you tak ikat. Oh, you tak guna ni maksudnya saya suruh ni kat sini. Ni, ikat sini. Lepas tu nanti dia ni. Sekejap sana. Macam ni. Okey, lepas tu nanti you biar dia macam tu. Lepas tu you pergi belakang. Okay, make sure is what we call is straight and ni. Okay. Okey, ni.
Series number 1121.
Tak tegang ni. Cuba tak payah cakap. Okey, dengar macam ni je. Saya dah dengar tak? Saya cakap
1121.
tu kuat you cakap. Dengan sama je intonasi yang you cakap tadi. Okey, cuba dengar macam ni. Cuba tanpa guna ni, cuba dengar tak dia cakap. Cuba buat suara tadi. Tak tanpa guna tu. Ni. Dengar tak? Dengar tak dia cakap Okey. Okey, cuba buat. Tak tegang ni. Tak tegang. So basically you mainlah nanti. Pandai-pandailah you main dekat kampung ni. Because this basically the idea is that even this, if let's say I try to disturb this disturbance, for example let's say hujan ke apa, this like this tau. Kalau saya pegang ni macam hujan tau. You cakap dia akan getaran tu akan sampai sini, dia akan masuk kat saya. So dia tak pergi sana lah. Bila dia loose pun tak adalah getaran tu masuk kat saya. Maksudnya you disturb the vibration lah. That's why this must be very tight, this thing also is not good lah because this is stretchy. Normally when you want to do this, you need to find some material that is not stretchy. Okay, not stretchy. Then you can clear very well lah because when you stretch, this thing will bounce back like that. So it's not really good lah. Loose also not good. If you hold the hand also not good. So that's why you must be just the string like that lah. So if you want to cheat in the exam, you can use that lah. Okay, so mana saya punya ni? Okay, so this is the antenna. The antenna that you see. Ni mana saya punya notes? Saya tak tahu mana notes saya. Saya bawa notes tapi saya tak baca pun. Okay, so this thing. Okay, so this thing is what you call the antenna, not antenna, the cell tower. The cell tower across the globe. So you can see if let's say I go. Okay, here let's say I go there. Cell tower map. Ada ke? Cell tower map. Saya tak tahu ada ke tak. Cell tower map. Semalam internet tak ada Saya buka YouTube Dah okey ni kan? Okay, let's say I go to here, cellular tower and signal map. So we go to see Malaysia part in UAE Okay. So here tak nampak lah. Okay lah, whatever. Dia tak ni lah, dia tak properly ni. So I need to make it big, small like this. Okay, let me macam ni. Salah. So dia lain dia punya ni. Okay. Anyway, so network. Okay, like this. And then go here. And let's say I go select provider. Let's say we go to our place, this here, UAE. So here UAE. Let's see UAE. So let's say we see the what I call provider. Provider, this is not in Malaysia yet. This network, this still not Malaysia. Because they are not this. Because they are not full size ni. Dia tengok macam ni. So general. That's why they are not really set carefully lah. Because I don't see this, what the thing. You can see but I cannot see. Then put here lah. Let's see here. By the way, this also use wireless transmission. This, from this to my computer, they use 2.4 gigahertz in terms of like the what you call the energy. Because when you know the frequency of the wave, you will know the what you call the wavelength. Later I will show you. But for now, I want to get this right first. It's difficult when you So here, provider detail, close, menu, general, advertisement, whatever setting. OpenStreetMap, what's new, location search, location tower search, So basically network provider, there are a lot because they don't have telecom here. Let's say DG, ada DG tak? They put everything, so they don't. I need to set to. Wait. Cellular coverage map, cell mapper. DG kan. Okay, so kalau you tengok sini, you pergi dekat URA, you can see this is where the cell tower is located. One in the Salahuddin, you can see is staff quarters here. So there are one cell tower here. That cell tower is from DG, from DG, and the cell tower in front of your entrance. There are also another cell tower. But if I go for here, and then if I go here, and then I go to, let's say, Cellcom. What is Cellcom? Oh, dia ada nama. Malaysia. Cellcom. You see the Cellcom is different. So you can see the Cellcom is around at Sadina Hamzah and here. And if I go to other thing and so on lah. So you can see where is the cell tower is located. If I go for everyone, let's say everything, every provider, you can see is this just for the Cellcom lah. So you can see there are 14, 10 here, 3 here, 13 here, 7 here, 3 here, 1 here, and so on. So basically it's distributed across the region lah, to allow you to to receive the call instantaneously. So that is the cell tower. If you look here, if let's say I go click one very clear. What is the URA? Okay, let's say I click here. I click somewhere here. Okay, you can see here the all the detail lah, all the details. So for example, let's say cell 11 whatever, the system subtype LTE. LTE is basically stand for long term evolution, meaning that when you have LTE is 4G lah. 4G. If you have GSM, that is 2G. That's 4G and 2G is generation. Here, if you look here, let me go here first for a while. Here, this 4G and 5G, whatever this thing, the one that you normally hear, is nothing to do with the gigahertz whatever. It's just generation. Don't make mistake. This is generation. Okay. Nowadays, we use your phone use 4G. So LTE, you see the tower just now, they are LTE. LTE, they use the 4G. This 3G and 2G is under GSM. Okay, so basically, what I want to tell you is that this 4G or 5G, whatever this thing, doesn't have anything to do with the gigahertz here. Okay, most people make mistake that thinking that 5G is something very new lah. Because if you look at your home Wi-Fi already use the 5 gigahertz. So it's not generation, it's gigahertz. So 5G, even though it's 5G, the band where it's operate, the wave that they operate is beyond, is here, 26, 66, 40, and around here lah. So generation is not gigahertz. Doesn't mean 5G use 5 gigahertz. 5 gigahertz is here. But 5G, the actual 5G that nowadays people talk about 5G, they will use at high frequency band. When they use at high frequency band, what happens? When something is high frequency, it's more energetic. So that's why there are a lot of concern by people that whether this thing will affect you in some way because it's more energetic than the normal 4G here. But if you think about it, the light itself in terahertz is much more much more higher than this. Still nothing happened. So yeah. So that's about that thing. But coming back to this 4G thing, what is the thing? I need to go back. So if you look here, you can see a lot of things. The cell, blah blah, and so on and so on. So this is megahertz, whatever. This is just the thing lah. The bandwidth 10 megahertz. Is 10 megahertz the energy that they use, and then they also have what we call signal strength. This 71 dBm. What is dBm? What is dBm? M apa M? What is M? Because this, I refresh back the prefix that you learned before. So decibel. This just to refresh your prefix, your prefix what you learned before. So what is dB? You heard before, right? dB. What is dB? dB stands for decibel. You know deci is what? 10 to the power of -1. Bel is what bel? Bel is what bel? Unit of what? Okay, bel is not really unit of the sound. Bel, because if you think about it, this signal strength, signal dBm, it doesn't have anything to do with the sound. So bel is basically, it's a ratio, it's just a ratio. It's just a ratio, it's basically, we call it a power ratio lah. It's just a power ratio. Power ratio. Okay, so basically you have power 1 over power 2. Power 2. So basically, decibel mean 1/10 of bel. 1/10 of the ratio. So it's not unique to sound. People use for sound because decibel, this decibel, the reason why they use this decibel unit is because to what we call to deal with the big and very big or very small number. Let's look here first. The bell, not deci, the bell is a power ratio. Power 1 over power 2. For example, let's say you have something power, let's say 100 milliwatt. 100 milliwatt. Let's say power number 2 is 10 milliwatt. So you get what? You get 10 milliwatt. Okay. So that is the thing lah. But this thing, this power ratio here, the bell power ratio is not just simply a ratio like this. It's basically logarithmic power ratio. Meaning that in front of this you need to put log. You need to put log. So when you heard, suddenly you see log, your mind start to blank, right? Because log, we are not used with the log. Log is basically when you don't have linear scale. Linear scale, if you have something like this, you have, let's say, this 1, 2, 3, 4, 5. We are used to this. But log is like this. Maybe 1, suddenly 10, suddenly 100, suddenly 1000. So meaning that this distance is the same, but the value is totally not linear, right? It just like goes exponentially out. So for this is linear, the difference is linear. So this is linear scale. This is log scale. So bell is basically logarithmic power ratio. For example, if you have 100 milliwatt as a power 1 and 10 milliwatt as power 2, if you put log here, log this thing, you got equal to log 10. What you get? Log 10 MV. Because this you can use your calculator lah. You will get what? You will get 1. 1, right? 1. Okay. Because as a engineer, because I don't want just to what we call to talk about wave, just something simple like that. You need to also know a little bit about the calculation. You are biochemical engineer. So the engineer part, you need to be at ease when you are facing this mathematic thing. So log 10 equal to 1 lah. So that is 1 bell because we talk only bell here. But in terms of decibel, how much? How much in terms of decibel? Just to see the conversion of formula. In terms of decibel, how to get decibel? 0.1 or 10? Because decibel is basically the decibel is basically 10 to the power of -1 bell, right? And then you have something bell here, whatever bell here, let's say X bell. Okay, in order to convert, so we put X bell here. So in order 10 bell, decibel is basically 1/10 of the bell, meaning that 1 decibel equal to 110 is 0.1 bell, right? In order to cancel out this thing, the value. So you do like this, you cancel out this value. So basically this will go up lah. So in order to what we call, when it goes up, you get decibel is basically 10, whatever this thing lah, 10 bell lah, 10 times to log power 1 over power 2. Okay, so that is basically the formula lah to get the decibel. So this times lah, this 10 times this thing. Okay tak? Okay tak? Kalau tak okey, kita masuk matematik dah tak okey eh? Okey tak? Umi atau dah tak okey dah? Okey eh? So okay, my question now. Okay, so this is the example eh. My question, this for bonus for bonus part to see whether you pay attention or not My question now. Apa question saya? Okay, how many dB how many dB you increase when you double the power. So that's the question. How many dB you increase when you double the power? So here the example is there is 100 milliwatt, right? The power, this power. So 10 is another power lah, reference point lah. So if let's say you want to compare two things, one is double than the others. How much in terms of power is double, but in terms of bell, how much it double? Understand or not? For example, let's say you have 100 milliwatt, you double, you get what? 200 milliwatt. Okay. So let's say from here to here, how many decibel change? That's the question lah. From 100 milliwatt to 200 milliwatt, how many dB change? Anyone 1 point? You can come here and say 1 point. It's quite easy if you pay attention. It's not so difficult lah. I mean this power 2 or whatever, this is just a reference lah. So when you increase a power, double the power, how many bell you increase? So that's the question. So this is what we call the formula for that. dB is equal to this. How to get that? How many bell you increase when you double the power? That's the question. You can, Nak ke depan. Kalau salah tak dapat apa-apa. It's sama juga if let's say you have 10 milliwatt to 20 milliwatt, double, right? So the same idea. So kalau salah tak dapat. You can write here lah. Give you justification and how many bell you increase when you double the power, because I want to see whether you can understand the what we call the equation. The equation is given, so you can see this is like mathematics lah. The equation is given, whether you can solve it or not. Tak apa, nak tahu apa log, bagi tahu Umi akan kira.
This one is 200 divided by 20 is also 10. So log 10 is 1.
Okay, thank you. You get 0.5 only lah. Tak boleh dapat penuh Akmal. Okay, basically like this. The way how you use it, this is the power 1, this power 2 is just anything lah. Now you want to compare between, let's say 100 to 200. So basically you are compare something that have a same reference, this thing. should be same lah, because if you want to compare this thing, the power too must be same lah, because you want to compare apple to apple. So if let's say you have this, instead of whatever, let's say dB, let's say I put this, penuh lah. So basically it's dB equal to 10 log, okay, here is the key lah. Whether you divide or whatever, let's say this power 2 is constant lah, let's say we put 1 lah. So let's say this, 100, instead of try to divide, so this is basically I divide by 1. So because I want to compare with dB, 10 log 200. 200 also divide by 1. Because I want to compare apple to apple. This, you don't compare apple to apple because you divide by something, reference point is different. So it's not, jadilah. So log 100, berapa lah Umi? Berapa Rohani? Log 100. 2. So you get 2, right? 2 times 20, you get 20. 20 dB kan? This one? Log 200 berapa? 2.3 times 10? So you get 23 dB. So the difference is 3. The difference is 3 dB. So that's why this is the difference between linear scale and the log scale. So even though here in real life you increase double, but the decibel that you increase only plus 3 dB. Understand or not? Okay or not? So that's why you see, instead of using a big number like this, they use a small number like this to show the change in something. So this is useful when you are dealing with something very big or very small, because instead of writing 1000 whatever milliwatt now, and then compare this with the 10,000 milliwatt. So instead of doing this, you can say, okay, the difference is 3 bell, like that. 3 decibel. That's why sometimes you see the use of this decibel throughout the thing lah, -70 or whatever that thing. So that is basically decibel. So that is decibel. So I will what we call, just add a little bit about decibel, because now I don't want to go something new, because it's already 11:15. So I will continue a little bit about decibel and then we wrap up lah. So decibel here, this, as I said, bell is basically logarithmic power ratio. Normally you heard about decibel when you use decibel when you sound, right? Normally for sound, right? For example, this thing, how much, for example, Azim talk, how much loud Azim talk. So that also you can use decibel. But that, when we use that, it's not about power, because that is non-power. Sound level is not power. This power, milliwatt is a power. Milliwatt is a power. So bell by itself is a power ratio. So how come people use decibel for something that is non-power related, like sound level? Okay, you know that normal human speaking is around what? It's around 50, 60 decibel. So how come that's happened? Because it's not power. So for that, you need to see here, because power, power is basically, power apa? Power is voltage squared over resistance. Okay, this is power, the power equation lah. Because we have this formula, dB equal to 10 times log power 1 power 2. Okay, so this is okay if you use it to deal with something that is power. So you use this formula to deal with this, because the M here is basically decibel, milliwatt, whatever lah, power lah. But when you have sound, okay, sound is not a power properties. It's not power lah. It's not power properties. So that in order to use decibel, which is this thing, decibel, which this thing, you need to relate non-power properties, non-power properties, properties. So in order to use decibel in sound, you need to relate to the power, because as you can see here, the voltage is squared. Okay, so in order to relate, so whatever you want to use, you need to sort of like square it also. Roughly, you need to square lah in order to, because the power correlate to the voltage squared. So basically, it's as if you have something like this. You have something log value, because we are don't use value 1, value 2, and then you have this, let's say this 10 dB. So instead of like this, if you have squared like this, because you want to convert, because if you have power only, you can use this. But if you don't have power, you need to sort of like relate with something, the equation of power lah. So you see the equation of power, this and this is correlate with each other. So you need to, so this as if you square here. You square here. So you do the log thing, is basically you take it out, so basically you times 2 lah. So this become 20 log value like that. So this is basically formula for what we call decibel when you deal with non-power properties. So the question now, okay. So I want to relate this with the sound, because we deal with the sound here, with the sound. So sound is basically, why we hear sound is because of the pressure in the atmosphere, the change in pressure in the atmosphere lah. So it's basically a sound, what we call sound pressure level, SPL, sound pressure level. Okay. So basically, you hear sound because there are pressure difference in the air lah. I talk something like this, there are pressure different around you, so you hear the sound lah. So normally, the what we call, okay, human ear, they can detect the sound between, because pressure, this is unit, the human ear can detect the sound from 20 micropascal to 20 Pascal. 20 Pascal. So this is basically the threshold of human ni lah. So this is basically the pressure. So you know when you have pressure, you rasa sakit kan? Pressure you tekan. So this 20 Pascal is the maximum threshold that human can bear. The highest threshold that a human can bear lah. So this is what we call the pain threshold. So this is like a very inaudible lah. So this is the what we call the change in pressure that human normally can hear lah. 20 micropascal to 20 PA. So you can see this is 10 to the power of negative 6. This is 10 to the power of negative 1, right? So you can see there are a lot of numbers, a lot of zeros there. So that's why people use decibel. If they don't use decibel, then it's very difficult lah to sort of like 2000, 100 like that. So there are many zeros. So in order to convert it to decibel, how you convert it? So if you want to convert this into decibel, 20 micropascal to decibel. So how you convert it? You use this formula. So dB equal to 20 log, let's say 20, let's say the lowest region here, so meaning that the value number 1 maybe 20 micropascal. So the reference, let's say we put this also 20 micropascal. So times, so you get this. So log this basically 20 log 1. Log 1 equal to 0. So basically 0 decibel. So basically this is the lower limit lah, 0 decibel. So the threshold is basically what? 20 PA dB equal to 20 log. So now you have 20 PA, and then you can divide with the reference, because you want to compare these two. Decibel is about comparing. So you want to compare also with 20 micropascal. 20 micropascal. So kira berapa dapat? So 20 log, what is this? 20 PA over this thing. 20, apa ni? 20 divide by, is basically 20 divided by 20 times 10 to the power of negative 6. How much is this? And try to log it. This thing. Because this is like a practice for your conversion. Because previous class we do conversion, so this conversion in real life lah. So how much this? 20 divided by 20 times 10 to the power of negative 6. And then you log this thing. Huh? 6. You get 6, right? When you do everything, after log, right? After the log, you get 6. So, meaning that 20 times 6 is 120 dB. So, this is the maximum around 120 to 20. So, if let's say I go to here, human sound decibel, human decibel. So, like that lah. 180 dB, so maybe it's higher lah. Maybe this threshold, the threshold that I use is around here lah. But normally at 120 is basically the sound of jet engine lah. So it's very loud. So 180 maybe much lah. So let's go to here lah. Got clear here. So maybe their picture. Normally their picture. So you can see what is decibel. This frequency. What is in decibel? Let's see image. Image. You got. Tak nampak ni. You got. Okay, you can see there. Extremely loud aircraft take off 120. So that's why how they get this decibel point is basically using this thing. Basically, because the actual thing, decibel is just the thing that people invent. But the actual thing, the sound is basically the vibration of the air, the change of sound pressure level in the air. That's why you hear sound. So that is the absolute thing. You convert, but 20 micropascal and so on, it's so difficult, right, to normal human to what we call to play around. Usually human, normally layman, they like this thing, simple, right? 10, 20, 30, 40, simple. But the actuality is like this. It's like a pressure, how much your ear can sustain the pressure. The pressure tekan kan, pressure tekan, the gedang to you tu, pressure, sustain the pressure from outside. So this is the human threshold lah, 20 PA like that. And this when we convert to decibel is, that's the thing lah, extremely loud, 120, and then this is 0 hearing threshold and so on. So today we wrap up the thing. So today we learn about wave. Wave have a lot of properties. Later on we will use this wave thing to sort of like probe into the small stuff lah. So in the next class we will continue about this thing, continue further about the wave, because later on when we talk about the tools, wave is the main thing, the fundamental basis of how we use the modern tool for probe the nanoscale. So next class is also about wave, continuation about this. But today you learn about how this thing from the science goes to the wave, the example of the wave, about the cell phone, how cell phone work, decibel, how to practice the prefix and so on, and that's it for today.